Hey everyone, and welcome back. Today, we are diving into one of the strangest, most powerful, and purely quantum ideas in all of physics, spin. It's a property that has absolutely no counterpart in our everyday world, but believe me, it is essential for understanding how everything works.
So let's just get right to the core puzzle. In our world, for something to have angular momentum, it has to be moving. Think of a planet orbiting the sun or a wheel turning. But what if I told you an electron, sitting perfectly still, also has angular momentum? It sounds totally impossible. It shatters the rules we're all used to. And that contradiction is exactly where our story begins.
So how are we going to unpack all this? Well, we've got a roadmap. First, we'll face that classical contradiction head-on. Then, we'll figure out what quantum spin actually is. After that, we'll learn the unique language physicists had to invent to even talk about it, see what happens when spin meets a magnet, and finally, look at the brilliant experiment that proved it all.
All right, Section 1, the classical contradiction. This is where we see how experiments with the electron revealed something that, according to the physics we know and love, simply shouldn't be happening.
Okay, so in the world we live in, the classical world, angular momentum, which we call L, is pretty straightforward. It's calculated from a particle's position, r, and its momentum, p. Now the key thing here is that p, the momentum. If a particle isn't moving, its momentum is zero. And if p is zero, well, its angular momentum has to be zero. No exceptions. That's the rule.
And yet, experiments just blew that idea right out of the water. They showed that even when an electron had zero momentum, it wasn't moving, it still had a very specific, non-zero amount of angular momentum. This was a bombshell. It meant there had to be a totally new kind of angular momentum, one that had nothing to do with moving through space.
And that brings us to the solution, a brand new fundamental property of matter called spin. And this isn't just some patch on the old theory. It's as core to a particle's identity as its charge or its mass.
The key word here is intrinsic. Spin is an intrinsic form of angular momentum. It's not something a particle does, it's part of what a particle is. Think of it like a fingerprint. It's just there, built in, a property it carries with it no matter what.
Now, the word spin is a little bit dangerous because it immediately makes you picture a tiny ball, spinning on its axis like a top. And while that's a helpful starting image, it's crucial to understand it's just an analogy. As the physicist R. Shankar points out here, we keep the name, but we have to ditch the mental image. There's just no consistent way to picture spin as actual mechanical rotation.
And get this property is totally unchangeable. The magnitude of an electron's spin is always 1/2 when you measure it in the right quantum units. You can't speed it up, you can't slow it down. It is locked in, a permanent part of the electron's identity.
Okay, so if you've got this brand new property that has no parallel in our everyday world, how in the world do you even talk about it, right? The old math just won't work. So physicists literally had to invent a new mathematical framework, a whole new language, just to describe spin.
This new language basically has three key pieces. First, instead of a normal wave function, you need this new thing called a spinor, which has two components, one for what we call spin up and another for spin down. Then, to actually do anything with this spinor, you need a new set of operators. And these new operators, well, they're represented by simple 2x2 matrices.
And here they are. These are the famous Pauli matrices, and they're basically the engine room of spin mathematics. When you scale them by the right constant, they become the operators for spin in the x, y, and z directions. It's incredible, but these simple little grids of numbers perfectly predict everything about how an electron's spin behaves.
So we have this abstract mathematical idea described by matrices. But what happens when it actually meets the real world? Next up, we're going to see what happens when spin runs into a magnetic field. Here's where it gets really interesting. A moving electric charge creates a magnetic field, right? Well, even though an electron isn't literally spinning, that intrinsic angular momentum, that spin, it does the exact same thing. Spin gives the electron its very own tiny, permanent magnetic field, which makes it act like a microscopic compass needle.
But of course, because it's quantum mechanics, there's another twist. When you compare the strength of the magnetic field from spin to the one you get from classical orbital motion, they're not the same. For the same amount of angular momentum, spin produces a magnetic kick that's twice as strong. This ratio even has a name, the gyromagnetic ratio.
This weird doubling effect is all wrapped up in a number called the G factor. For regular old orbital motion, G is 1. But for an electron spin, experiments show that G is almost exactly 2.
For a long time, this was just this magic number that physicists had to plug into their equations to make the math match what they saw in experiments.
But then came one of the most beautiful moments in all of physics. As Shanker mentions, Paul Dirac combined quantum mechanics with Einstein's special relativity, and out of his new equation, he didn't just find an explanation for spin, the equation demanded it. And what's more, out popped the G-factor, predicting it to be exactly 2, not as a guess, but as a fundamental consequence of the universe.
So what does this little quantum magnet actually do when you put it in a bigger magnetic field? Well, it doesn't just snap into alignment like a compass needle. No, that would be too simple. Instead, it starts to wobble, or precess, around the direction of the magnetic field. It's a lot like how a spinning top wobbles as it spins in Earth's gravity. We call this Larmor precession.
Okay, this all sounds really abstract. Matrices, precession. I mean, how could you ever prove any of this is real? That brings us to our grand finale, the Stern-Gerlach experiment. This was just an incredibly elegant piece of work that basically made the weird quantum nature of spin visible to the naked eye.
And this experiment is famous for a good reason. It was the smoking gun. It wasn't just another data point. It was the definitive, undeniable proof that this thing called spin was real, and that it was quantized, just like the new theory predicted. The setup itself was pure genius. First, they used a beam of silver atoms. Why silver? Because their total orbital angular momentum is 0, which means any magnetic effect you see has to come from spin. Second, they fired this beam through a special magnet that created a non-uniform field, stronger on one side than the other. This gradient is what actually pushes or pulls on the tiny atomic magnets. And finally, they just put up a screen to see where the atoms landed. And the result? It was breathtaking. A direct window into the quantum world. Classically, you'd expect a messy smear on the screen, as the random little magnets get deflected all over the place. But that's not what they saw. Not at all. The beam split perfectly into 2 distinct spots. This proved 2 huge things at once. First, yep, spin is real. And second, and maybe even more important, spin is quantized. It could only be up or down. There was no in between. It had to choose.
So in the end, spin isn't just some weird quantum quirk. It's the principle behind MRI machines. Its rules dictate how electrons build atoms, giving us the entire periodic table. It's absolutely fundamental. And that leaves you wondering, right? If a property as counterintuitive as spin was hiding in plain sight this whole time, what other impossible ideas are still out there, just waiting for us to discover them in the quantum realm?